Hello, Met 20-1. You are continuing your journey in sequences and series with Arithmetic Series, and you're going to hear about a famous young lad named Carl Friedrich Gauss. And this is about knowing the difference between a sequence and a series. And as you can see by the achievement indicators, we're going to be talking about a rule about developing the sum of an arithmetic series and what that actually means, right? All right, so we'll carry on. And to start, let's review about the things we know from yesterday. An arithmetic series is increasing if and only if. Well, if and only if, and I want you to pause here and go through and do these and then come back and see if you've got this. This is review from the stuff we did last day. All right, so an arithmetic series is increasing if and only if D, if and only if D is greater than 0. Why? Because as we talked about last day, we had Katie who said, well, you have to be positive if you're going up, you have to be adding a positive. And we had Kirby who talked about you going to the right, so D must be greater than 0 if you're going to the right. And we also had Tina who talked about adding a negative if we were going left, but we're going right, so it has to be D greater than 0. If you're decreasing, that means D would have to be less than 0. An arithmetic sequence stays the same if the frog jumps by 0. If the frog doesn't jump at all, you're going to stay on the same lily pad forever. All right? And the first term of a sequence is denoted as term 1. The symbol for the general term is term n. These are the basic notations that we need to have success. What we're going to look at now is if you look at this Pharaoh's head built of cans or this Super Mario or these chess pieces, what are the patterns, what are the arithmetic sequences of the rows of cans, and how many cans would it take to build these objects totally, right? Maybe we could have a project on that, all right? So we start this by looking at stacking some cans. So if we use a stock boy at Sobeys or and we think, well, if they want to build this Campbell's soup can, how many cans would it take? And how many cans are in each row versus what is the total number of cans in all the rows? So write a sequence generating the number of cans in each row. Pause and come back. So if you've now completed this page, so you've thought about it and you've written the pattern of cans. And if you think about it, obviously in the first row there is 1 can, the second row there's 2 and 3 and 4 and 5 and 6. And if we represent it like we talked about with our term formula, then any row would be 1 plus n minus 1 times d, or t1 plus n minus 1 times the common difference. In the next question, would the sequence be finite or infinite? And if you answered that, I would think that the best answer would probably be that this is finite because we aren't going to build an infinite row of cans. If there were 18 rows, how many cans would be in the 18th row? Well, pretty neat pattern because row 1 is 1 and row 2 is 2, so we can get that pretty simply. But now comes the question, well, how many cans in total would be in a stack of 18 rows? And now you've got to add up all these numbers. What strategies could you use? If you went through and you total them all up, it ends up being 171. Now, there's a few ways you might do that, and we're going to talk about that. But what if you had to do 100 rows? The 18 rows, well, that simply happens by you going 1 plus 2 plus 3 plus 4 plus 5 plus ... plus 17 plus 18. You have to add up all these numbers and that's going to give you 171. Now, I don't know how you did it. I want you to try that, how you did it, but there's got to be better ways. That's where our lesson comes in, right? The sum of the terms of an arithmetic sequence is called an arithmetic series. So when you take these terms here and you take these terms here and you put a plus sign in between them and you're now concerned about adding up all the rows of cans, you now have what's called an arithmetic series versus an arithmetic sequence that we talked about in the previous year. So in the sequence, you're only interested in the separate rows, but in the series, you're interested in the sum of all the rows. So what are some alternative strategies that you could use to solve this? Well, one method that you'll see here is, I guess, the rectangle method. If you stacked all the cans up into a row, clearly, if we only had 6 rows, we could clearly see that what would be the total number of cans? Well, it's not that hard to add up 6 numbers, and there'd be 21 total cans. But a way to help us in bigger questions would be, well, what if you made a rectangle and instead you stacked the number of cans and you look at the shaded region. Well, the shaded region for the rows of cans would obviously be 21, but if you built another pyramid exactly the same on top of it, you'd now have a rectangle. And when you look at the rectangle, that rectangle is got a width of 6 and it has a height of 7. And so if you find the total area of the rectangle, which is twice too much, you can clearly see the area is 42. So to find out the number of cans for the pyramid we want, we would just divide that by 2. So 42 divided by 2 is 21. So it's an alternative way using area to find the total number of cans used. If we use that idea if we use that idea and saying, well, I could build a pyramid with 18 cans, well, it would be 18 units wide, and then when you put it on top, when you put that on top, it would be 19 tall because you'd have one more on top, and therefore it'd be 18 times 19, but then you'd have to divide it by 2 in order for you to get the area. So that's the rectangle method of using it, right? So we could do it that way, but I like this way. One day, a famous young lad named Carl Friedrich Gauss, who I think was about 8 or 9 years old at the time, was given the question to keep him out of the teacher's hair. The teacher told him, would you please add up all the numbers from 1 to 100, dot, 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 all the way to 100. Now, she thought this would keep Gauss busy for a very long time, but it actually only kept him busy for just a few minutes, because when Gauss was asked to do this, he did not do it in the way the teacher thought he would. He didn't just add up the numbers 1 plus 2 plus 3. What he did was he simply went and said, what I've got is 101, and I've got 2 and 99, and I've got 3 and 98. And he paired all the numbers up. Well, when he made pairs, he said to himself, I'm only going to have 50 pairs. And every one of those pairs has a sum of 101. And so when you take 50 times 101, you simply get 5,050. And Gauss, in the blink of an eye, had the answer the teacher had hoped would take him a very long time. And then he was back in business again. Right, so that's another pattern we could have used with the cans in terms of adding up the total number of cans as well. And this is a lead-in into a formula that we use, right? So there's Carl Friedrich Gauss. A formula that we have, and you can see it here. So if you had this series, in general this works with all series. If you take that series and you reverse it and you put it below, and then you add the two series together, what you're going to end up with is pairs of identical numbers. You can see that in this sequence of numbers, you always get 26. But when you add that up, you should divide that by 2, because you're going to get, you don't really have pairs, you don't really have 6 pairs of 26 in one sum, you only have 3 pairs. So we divide that by 2. It's just a different way of doing it. We divide that by 2, and the sum of 6 is 3 pairs of 26, right? So the sum of 6 terms is really 78. This formula talks about the first term, adding the last term, and taking the total number of terms and dividing by 2. In general, the sum of n terms is given by the formula n over 2 plus n over 2 times term 1 plus term n. Whoops. And that's one of the general formulas for the sum of the number of cans or the number of oranges or whatever we're building in an arithmetic sequence. Now, this formula won't work for all of them, so some mathematicians decided that, well, Sometimes this formula is not going to be good enough. There's going to be situations that come up that require a different formula. And you notice that we already have a formula that talks about Tn, and you'll see that in a second. And Tn, we already learned that in 1.1 and 1.2, that Tn is actually a plus n minus 1 times d. So you can substitute this into, we could substitute this into that formula right there in order for us to change the way it looks, right? So if we do substitute in, you can see there is our Tn right there, and when you substitute that in, we end up with, when we rework it, 2a, or 2 times t1, and instead of right here, this might bother you a little bit, this is the same thing as writing 2 times t1 plus n minus 1 times d. That's used when you only know the first term and the common difference, but you don't know the last term, right? So that's going to be used in different situations. So this little note here is a disclaimer about when we can use this, okay? Right? Those are the times when we can use it. Arithmetic series, well, let's find out. Let's do a couple of examples. Determine the sum of the sum of the sequence 17, 12, 7, and so on. So the first thing you always do is look at your quantities that you know. You know term 1 is 17, you know term n is negative 38, and d is minus 5. You need to find out which formula would be useful. In this case, well, first thing we need to do is find out how many terms there are. Without that, we have no way of using either formula. So if I sub in what I know from last day into the Tn formula, I solve it and I find out that this sequence, when I get to 38, is going to have 12 terms. All right? Now I can pick the formula I want to use, and it makes the most sense to pick this one because I know the first term and I know the last term. So I plug in T1, Tn, and n is 12. I can find out that the sum of the sequence is minus 126. Good stuff. Lastly, we're faced with a bit of a challenge, right? We're asked in this question to find the sum of two terms of an arithmetic series is 19, and the sum of the first four is 50. And this is going to rely on us using our Math 10 knowledge and everything. So how are we going to attack this? The first thing we need to do is we need to take these two pieces of knowledge and make use of them to find out these two questions, right? So the first thing we write down is, what does that mean? Well, the sum of 2 equal to 19 and the sum of 4 equals 50. I write those down as two statements. Doesn't seem very helpful, but when I look at the formulas that I have to use, right, I say to myself, well, the sum of 2, if I plug it into this formula here, I know that that sum is 19 and it's two terms, but I don't know term 1 and I don't know the difference. But I sub in what I know and I simplify it to 19 equals 2 times term 1 plus d. I got two unknowns, but I can't solve that. In the other equation, I substitute into the sum formula up there, and I end up with 50 equals 4 over 2, and so on. I simplify this formula, and I get 50 equals 4 times term 1 plus 60. From Math 10, we're supposed to remember I've got two equations with two unknowns. That requires us to use the method of elimination, and we solve the system. So if you have to, you go back in your notes and you look that up. Solving that system, we simply use the equation 1, and I multiply equation 1 by 2, and I then line them up together and I subtract. And when I subtract, the t's blow up, and I'm left with minus 4d equals 12. That means d equals 3. I then can go back to the equation, substitute in d, and I find out that t1 is equal to 8. Now I can answer my questions. The first four terms is 8, 11, 14, and 17. And in B, the sum of the first 20 terms, because I now know all the unknowns, D is 3 and T1 is 8. And the sum of 20 terms is equal to 650. All right. I want you to carry on with your assignment, and we will discuss the notes and your assignments tomorrow.